Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. So far in this course, we have been talking about pure translation motion and pure rotation motion. But in general, if you consider any motion, that will have both these components. So as I said in the beginning of the course, there is an important theorem in classical mechanics which is known as Chase's theorem, which says that any general motion can be treated as a translation of the center of mass plus a rotation about the center of mass. Now what we are going to do is we are going to introduce the center of mass coordinates, which we are already familiar with, and using the center of mass coordinates we will be able to derive simple expressions for angular momentum and torque. So center of mass coordinate means you choose a coordinate system in such a way that the origin coincides with the center of mass of the system, and all the position vectors are now defined with respect to the center of mass. Okay. So now onwards, this is the coordinate system we are going to use. Okay. So as always, consider that your rigid body is made up of n particles with masses mj and a position vector rj. Here rj is measured with respect to your regular inertial coordinate system. Okay. So the angular momentum of the body is given as sum of the angular momentum of the individual particles. So total angular momentum capital L is sum over j rj cross mj rj dot. And we know the definition of center of mass. The position vector of the center of mass capital R is given as summation over j mj rj divided by capital N. Now we are going to introduce the center of mass coordinates. So if you take a simple two-body system M1, M2 with respect to an inertial coordinates, their position vectors are R1, R2, and capital R is the position vector of the center of mass. Now with respect to this point, I am going to define the position vectors of M1 and M2. So position vector of M1 in the center of mass coordinates is R1 prime, and position vector of M2 with respect to the center of mass is R2 prime. So R1 prime and R2 prime are the new coordinates with respect to the center of mass. Okay. Now if you look at this triangle, you can find that R1 is nothing but capital R plus R1 prime, and if you look at this triangle, R2 is capital R plus R2 prime. So this is the general relation between the inertial coordinate and the center of mass coordinate. So in general, I can write Rj equal to capital R plus Rj prime. So I'm going to rewrite this equation in terms of Rj prime. So substitute for Rj and Rj dot here. So this is going to be summation over j R plus Rj prime cross Mj into R dot plus Rj prime dot. Okay. Now expand this. So this is R cross summation over Mj R dot plus summation over Mj Rj prime cross R dot plus R cross summation over j Mj Rj prime dot plus summation over j Mj Rj prime cross Rj prime dot. Now we can simplify this further. Now if you take the second equation, you have a term summation over j mj rj prime. So let's expand this. Rj prime is nothing but Rj minus R. So you have summation over j mj rj minus summation over mj into R. Summation over mj is nothing but the total mass m. So the second term is minus mr. Now what is summation over j mj rj? This is nothing but m into r, right? So you have mr minus mr, this becomes 0. So the second term vanishes. Now if you look at the third term, summation over j mj rj prime dot. This is nothing but derivative of this term, right? Since summation over j mj rj prime is 0, its derivative is also going to be 0. So the third term also vanishes. So your expression gets simplified as L equal to r cross summation over j mj r dot plus summation over j mj rj prime cross rj prime dot. Now you can simplify this even further. Take the first term. Summation over mj is nothing but capital M. So this is r cross mr dot. And what is r dot? Rate of change of position of the center of mass, which is nothing but the velocity of the center of mass in the inertial system, right? Called as capital V. So this is r cross mv. So the expression for total angular momentum is capital L equal to capital R cross mv plus rj prime cross mj rj prime dot. Now what's the physical meaning of this equation? The first term in the equation is nothing but the angular momentum due to the motion of the center of mass. And the second term is angular momentum due to the motion around the center of mass. Okay, so first one is angular momentum due to the motion of the center of mass about the origin. Second one is the angular momentum due to motion around the center of mass. Okay. So you will find that these are the common terms or common types of terms in all the subsequent equations. Now, since we are talking about rotation around the z direction, the axis of rotation is always taken along the z direction. I can write down the z component of the angular momentum as Lz equal to r cross mvz. This is the z component of the first term plus the z component of the second term. Now we can simplify the second term if we treat it as pure rotation around the center of mass. So consider a rigid body, a cylindrical rigid body. So this is the position of the center of mass. So and if you take an axis which passes through the center of mass, you will find that the axis is in the z direction. Now consider a particle mj. So this is the location of the particle mj, and in the center of mass coordinates, its position vector or position with respect to center of mass, this is the rj prime vector. Okay. Now since this is at an arbitrary angle, you can resolve it into a parallel component and a perpendicular component. Okay. And since we are talking about rotation around the z-axis, if you look at the parallel component is in the direction of the z-axis. Okay, so in our analysis, this is not going to count much because this is in the direction of the axis of rotation. On the other hand, the perpendicular component, this is the one which is going to give us a sense of rotation around the z-axis. Okay, so we can, even though mathematically we need to write rj prime as a sum of parallel and perpendicular component, in the case of pure rotation, we are going to consider only the perpendicular component, and the perpendicular component here is denoted as rho j prime. So I can rewrite this equation in terms of rho j prime. Okay. So summation over j mj rj prime cross rj prime dot, I can write it as summation over j mj rho j prime cross rho j prime dot, because rho j is the component which gives you the pure rotation. Okay. Now we can we can simplify this even further. So rho j is the radius, rho j prime dot is the velocity. So in the case of pure rotation, we know that radius and velocity are always perpendicular to each other. So you can replace cross product with a normal product of the corresponding magnitudes. Okay. Now, so this is going to be summation over j, mj rho j prime into rho j prime dot. And rho j prime dot is the linear velocity, right? So in the case of pure rotation, I know how to convert linear velocity into angular velocity. It is simply linear velocity equal to radius multiplied by angular velocity. So rho j prime dot is nothing but radius rho j multiplied by angular velocity omega. So the second term gets simplified as summation over j mj rho j prime square into omega. And summation over j mj rho j prime square is nothing but angular momentum of the system about an axis which passes through the center of mass. So this is nothing but your I naught, right? So the second term gets simplified as I naught omega. So the total angular momentum along the z about an axis which passes through the z direction, Lz equal to I naught omega plus r cross mvz. So if you look at this equation, the first is nothing but angular momentum about the center of mass, and the second term is the angular momentum of the center of mass about the origin. So you can say the angular momentum of a rigid object is the sum of the angular momentum about its center of mass and the angular momentum of the center of mass about the origin. In general, these two terms are referred as the spin term and the orbital term. So motion around the center of mass, this is the spin component. Motion of the center of mass around the origin, this is the orbital component. I can illustrate this with the example of Earth's rotation. You know that Earth is rotating around the Sun in a particular orbit. Earth also has its rotation around its own axis, right? So we are talking about two rotations. So in this case, rotation of Earth around its own axis, this is known as the spin motion, and rotation of Earth around the Sun in the orbit, this is known as the orbital motion. So this is true for many other physical systems. For example, if you consider an electron in an atom, so electron has two types of angular motion. One is the motion around the nucleus. This is the orbital motion. Then electron has rotation around its own axis. This is known as the spin motion. So consequently, electron will have two types of angular momentum. One is the spin angular momentum and the other one is the orbital angular momentum. Since angular momentum has two components, the torque also is going to have two such components. So let's see what are the expressions for this. So I can write in general torque tau equal to summation over j rj prime cross fj. Now I can write rj in terms of rj prime and capital R. So this is going to be summation over j rj prime plus r cross fj. Expand this, summation over j rj prime cross fj plus r cross summation over fj. Now summation over fj is the total applied force capital F. So second term is capital R cross capital F. So once again you can see that the first term in this equation is the torque about the center of mass due to various external forces, and the second term is the torque due to the external force acting at the center of mass. So one is the torque around the center of mass, second one is torque due to the center of mass. So you have once again two terms. One is the orbital term and one is the spin term. Now if you consider fixed axis rotation about the z axis, so I am going to consider the z component of the torque now. So let me say the z component of the first term, let me call it as tau naught, and the z component of the second term is r cross fz. So I can write tau z equal to tau naught plus r cross fz. Since we already know the expression for angular momentum Lz, we can calculate what is dLz by dt. So this is going to be I naught into d omega by dt plus d by dt of r cross mvz. Now d omega by dt, rate of change of angular velocity is angular acceleration alpha. So first term is I naught alpha. And in the second term, r is a constant, m is a constant, dv by dt is a linear acceleration a. So second term is going to be r cross ma. And we know that rate of change of angular momentum dLz by dt is nothing but the torque tau z. So I can equate this expression with the expression for tau z. So tau naught plus r cross fz equal to I naught alpha plus r cross maz. And m into a is nothing but the total applied force capital F. So the right hand side becomes I naught alpha plus r cross fz. Now you compare the left hand side, right hand side. The second term is common. You can cancel that. Then you get tau naught equal to I naught alpha. So this is a very important relation, because from this you can infer that the rotational motion about the center of mass depends only on the torque about the center of mass. It is independent of the translation motion. So as we know, any general motion can be decoupled into a rotational and a translational motion, and these two motions are independent. That's the meaning of this equation. Since torque and angular momentum have two components, consequently the kinetic energy is also going to have two components. Let's see what are those. So start with the general expression for kinetic energy, K equal to half into summation over J mj Vj square. And what is Vj? Vj is nothing but Rj dot. So Rj dot I can write as capital R dot plus Rj prime dot, and since we are talking about rotation around the center of mass, is only the perpendicular distance is important, so I can write it as R dot plus rho j prime dot. Okay. Now substitute it back into this expression. So instead of Vj square, I can write rho j prime dot plus r dot square, and r dot is nothing but capital V. So the expression becomes half into summation over j mj rho j prime dot plus capital V square. Expand this, half summation over j mj rho j prime dot square plus half mj rho j prime dot V plus half summation over j mj V square. We have already shown that summation over j mj rj prime dot is 0. So same way summation over j mj rho j prime dot is also 0. So the second term vanishes. Then if you look at the first term, rho j prime dot is nothing but the linear velocity, which I can write as radius multiplied by angular velocity. So rho j prime dot is nothing but rho j into omega. So first term becomes half summation over j mj rho j prime square omega square plus the last term half summation over j mj v square. Summation over j mj rho j prime square. So in the case of pure rotation, this is nothing but the moment of inertia about the center of mass, I naught. So the first term is half I naught omega square. Summation over j mj is the total mass capital M. So the second term is half mv square. So once again you find that kinetic energy also has two components, where the first component is is related to the rotational motion around the center of mass. So this is nothing but the spin component, or more precisely kinetic energy of the spin motion. And the second component is related to rotation of the center of mass around the origin. So this is the orbital component, or the kinetic energy of the orbital motion. So in the case of a general motion involving rotational and translational component, all the important parameters are going to have two components, the spin component and the orbital component. So if you compare pure rotation with rotation plus translation, so this is the summary. So in the case of pure rotation, the equations are very simple. You take any linear equation, replace all the linear terms with the corresponding angular terms, you get the corresponding angular equation. So L equal to I omega, tau equal to I alpha, k equal to half I omega square. Whereas in the case of rotation plus translation, so in addition to these terms, you are going to have an extra term that arises due to the orbital component. So Lz equal to I naught omega plus r cross mvz, tau z equal to tau naught plus r cross fz, and k equal to half I naught omega square plus half mv square. Now let's analyze a couple of physical systems which have both rotation and translation. First one, calculate the angular momentum of a uniform wheel of mass m and radius b rolling uniformly in the clockwise direction without slipping. Okay. So let's assume that it's rolling in the x direction. The rotation is in the clockwise direction. Let omega be the uniform angular velocity. At the position vector of the center of mass with respect to the initial system is capital R, and capital V is the velocity of the center of mass. Okay. Since the radius is b and mass is m, the moment of inertia about the center of mass I naught equal to half mb square. And the angular momentum about the center of mass, angular momentum is nothing but I naught omega. So this is going to be half mb square omega. So L naught equal to half mb square omega. Since this is clockwise rotation, if you look at the direction of angular momentum, it points into the plane of the screen, which means you need to give a minus sign here. So L naught equal to minus half mb square omega. And what about angular momentum of the center of mass about the origin? So this is the second component, r cross mvz. Since the radius of the wheel is small b, and the radius and the velocity, so these two are perpendicular to each other, so you can replace cross product with a normal product of the corresponding magnitudes. So even though this is the total r vector, but in the context of rotation of the wheel, the relevant distance is nothing but the length of the radius of the wheel b. So this is going to be mbv. Once again, since the angular momentum points into the plane of the screen, I put a minus sign here. So this is minus mbv. So the total angular momentum about the origin is nothing but the spin component plus the orbital component. So this is minus half mb square omega plus minus mbv. And if you look at the rotation of the wheel, so this is a pure rotation. So I can write linear velocity v as the radius b multiplied by angular velocity omega. So in the second expression, substitute for v, so it becomes minus mb square omega. So Lz equal to minus half mb square omega minus mb square omega, which is minus 3 by 2 mb square omega. Let's do one more quick problem. A uniform drum of radius b and mass m rolls without slipping down a plane inclined at an angle theta. Find its acceleration along the plane. Okay. So once again, you have a wheel of mass m and radius b which is rolling down. So alpha is the angular acceleration, and which is the rotational part, and a is the linear acceleration, which is the translation part. And what are the various forces acting on the system? There is always weight W acting vertically downwards. Since this is rolling on a surface, there is a normal surface N which is acting vertically upward with respect to the inclined plane, and there is always a frictional force which acts against the translation motion. So these are the various forces. Okay. Now let's write down the equations of motion. First one, let's consider the translational motion, translation of the center of mass. Okay. So since W is at an angle theta, I can resolve into a parallel component and a perpendicular component. Since we are talking about translation motion along the plane, we need to consider only the parallel component. So the parallel component is going to be W sine theta. So if you take the rightward direction as positive direction, so W sine theta is in the positive direction, then you have F in the negative direction. So left hand side is W sine theta minus F, which is equal to mass into acceleration. Acceleration points in the positive direction, so the right hand side is positive. Second, let's consider the rotation around the center of mass. So what are the forces here? You have a normal force in the vertically upward direction, so that will be compensated by the vertical component of weight. So these two cancel, you don't have to bother about it, so you need to consider only the frictional force. Okay. And the frictional force, since B is the radius, F is the frictional force, the torque is nothing but radius, the cross product of radius and this force, so B cross F. Since these two are perpendicular quantities, the cross product will be replaced by a normal product of the corresponding magnitude, so this is BF. So I can also write the torque in terms of moment of inertia as I naught alpha, right? So BF equal to I naught alpha is the equation of motion corresponding to the rotational motion. Since the wheel is rolling without slipping, I can also write a relation connecting linear acceleration A and angular acceleration alpha. So this is the standard equation. Linear acceleration is radius multiplied by angular acceleration. So A equal to B alpha. So these are the three equations. Now I can solve this. From the second equation, I can write F equal to I naught alpha by B. So substitute that in the first equation. So W sine theta minus I naught alpha by B equal to MA. Since I am talking about a wheel which is similar to a disc, I naught is half mb square, and from the third equation I can write alpha equal to A by B. So put all this back into the first equation, it becomes W sine theta minus MA by 2 equal to MA, and weight W is nothing but mass M multiplied by acceleration due to gravity G. So mg sine theta minus MA by 2 equal to MA. So simplify this, you get a simple expression for linear acceleration A as A equal to 2 by 3 G sine theta. So that's for today. Thank you.